Okay, it's 7:30 and we're going to get started. Welcome to the December meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of the JSCAS, and here's our agenda for this evening. For our main speaker tonight, we have Dennis Webb with The Scale of the Universe in the Amateur Eyepiece, an Observing Plan for 18 Orders of Magnitude. Then I'll be bringing us, for the first time, three members' minutes in a row. First one will be our first annual JSCAS Astronomy Banquet. We'll talk about 2020, a year of astronomy for the JSCAS, and then I will be showing you some images from the Eldorado Star Party. And then we'll wrap it up with Chris Wells with Star Party News. If you have questions for our presenters, you can either enter them in as a YouTube comment if you have an account that will allow you to do that, or you can email questions to the presenters by the email address shown at the bottom of the screen, jscaslive@gmail.com. Trevor Quinn will be gathering up those questions and providing them to our presenters. So before Dennis gets started, I'd like to tell you a little bit about him. Dennis Webb was president of the JSCAS for 2 years in the 1990s and was a longtime participant and volunteer at the Texas Star Party. He became an amateur astronomer because of friendships in JSCAS. He is co-author of 7 astronomy books, including Annals of the Deep Sky, now published by American Astronomical Society. In 2008, he retired after a 36-year career at NASA JSC, where he had worked on Skylab, Space Shuttle, International Space Station, and Constellation programs as an engineer and manager. After retirement, he moved to the Dallas-Fort Worth area and is a member of the Fort Worth Astronomical Society, originally founded in 1949. With that, I'd like to turn it over to Dennis Webb.
This club was very important to me, being an amateur astronomer, and I guess I've been a member for 30 years. I'm very grateful that I don't have to pay dues, because I keep forgetting to pay dues to my local club. So hi to all my old friends. Some of you have heard this talk 30 years ago, but you'll just have to suffer through it. Okay, let's go to the presentation. All right. When I started out, I'm a curious guy, and once I got over the hump of basically taking an object, being able to point the telescope to it and look at it, I tried to look for additional meaning in these things. And so one of the things that was baffling to me was, how big is the universe and how far away is all this stuff? And you can look it up. Well, this is so many light years away and stuff. So I thought I'd try to organize it into an interesting observing plan. You look at objects at many orders of magnitude of distance away from the Earth. And so in this sequence, each object in the sequence is 10 times further away or thereabouts from the object before it. And so they work as signposts in kind of understanding. And in some years, you can see them all at the Texas Star Party, but the planets, you don't always get to see them. Part of the reason I wanted to do this was, I'd read about the distances to things, but I didn't have any intuitive sense of what that means. I mean, what does a million light years mean? It's just, it's 10 times more than 100,000 light years. But so I picked on this idea of order of magnitude. Also, in the short list of objects I've got, the object names kind of reveal the history of astronomy. And as we go through the list, you can see the effect of distance on size and visual magnitude. So what is an order of magnitude? Well, it's 10 times. So we got 1, 10, 100, so forth. Well, where does that come from? Well, we all take for granted our numbers, but the base 10 is based on the fact that you've got 10 fingers. Well, if we were the Teenage Mutant Ninja Turtles, they have 3 fingers on each hand, so you might have base 6. Or if we were using a number system used by the Aztecs, who count all the fingers and the toes, their orders of magnitude are 20 times. So I'll stick with 10 because I've got 10 fingers. It's a blessing. So let's start with the closest astronomical orders of magnitude, the easiest thing, because I wanted to pick objects you could mostly easily see. The first is the moon, which is 240,000 miles away, and it takes 1.3 seconds for the light to get from the moon to our eye. I looked for something that was 10 times further away than the moon, but there really isn't anything reliably in the sky. They're those scary Earth-crossing asteroids. But since they're not there, I just have a question mark. If you see anything there, let me know. 10 times further away from that is the planet Mars at closest approach at about 35 million miles away, and it takes the light 3 minutes to get from Mars to our eye. 10 times further away than Mars is Jupiter at closest approach at 372 million miles, and it takes 30 minutes for the light to get from Jupiter to our eyes. And 10 times further away from that is the planet Neptune at 2.7 billion miles away, and it takes 4 hours for light to get from the planet Neptune to our eyes. Then, okay, what's 10 times further away than Neptune? Well, nothing that we know of. Well, what's 10 times further away from that nothing? Nothing that we know. Well, what's 10 times further than that? And so you have this gap of 3 orders of magnitude between Neptune and the next closest object we can see. And that 8th order of magnitude is about a light year. So you can see we're talking incredible expanses of distance here. And here's a little graphic I stole that kind of talks about that. You got the inner solar system at the right, so you can see, yeah, if Earth is close to Mars and Jupiter, Jupiter is 10 times further away than Mars is. Then if you look at the next panel over, you can see Neptune. It's not labeled on the chart, but it's the blue ring. And then that's Neptune. That's the last one we can see. It takes you about 3 orders of magnitude to get out to what is the Oort cloud, which is the lower left panel. That's this ring of icy things that wasn't really known about until the last century. So when were these things named? Well, the moon was named in antiquity. It maybe had different names, but it's always had a name. Mars was named in antiquity, as was Jupiter. Neptune wasn't discovered until 1846, and the Oort cloud, if it's there, not that you can see it, was first postulated and discovered in 1950. And so as we go further and further away, there's this general theme that things are going to get dimmer and they're going to be discovered more recently. Trevor, we have any questions? Okay.
Not yet.
Okay. So after we leave the Oort cloud, we're in what I call the foothills of the deep sky. And so, as you might expect, the next closest thing we'd find would be a star, and that's Barnard's star at 6 light years away. Roughly 10 times further away than that is the star Castor in the constellation Gemini. It was known and named in antiquity. And it's 45 light years away. And then the Coma star cluster, the thing that's a big naked eye object, it was known of in antiquity. And it's 270 light years away. And obviously I fudged a little bit, but it's roughly an order of magnitude between each thing. So trying to understand this. Okay, Barnard's star is 6 light years away, so the light left Barnard's star when Lisa Simpson was born. Castor, 45 light years away, the light left it, that we see now, left it when Homer Simpson was born. And the light left the Coma cluster, star cluster, 270 years ago when Isaac Newton was born. So, okay, we're now we've left the solar system. We're out wandering around in the nearby part of the galaxy, and the orders of magnitude are very useful for understanding galactic structure. The Trifid Nebula, Messier 20, is 5,000 light years away. The Hercules Globular Cluster, 22,000, and a globular I'll talk about a little more, NGC 7006, is 195,000 light years away. So we've gone from Homer and Lisa Simpson to 195,000 years. So what does this distance mean? Well, the Messier 20 distance in light years is roughly the width of a spiral arm. The Hercules globular cluster is roughly the same distance from the Earth as the galactic center is. And then this NGC 7006 globular is roughly twice the diameter of the Milky Way galaxy, and it's equivalently the distance to the Magellanic Clouds. Now, that's why I picked this globular, because I read about it, and it's called an intergalactic tramp globular, because it's in the gravitational system of the Milky Way, but it's beyond its usual borders. And so also, as you look at these, the size gets smaller as you get further away, like you might expect, and the magnitude goes up or down, or, well, it becomes fainter. So another way of going back to the time thing, here's a nice picture of that, in this beautiful visualization of the Milky Way galaxy from the outside by JPL. So you see us as the little heart, and then there's that Messier 20 on the other side of the spiral arm, and Messier 13 kind of out off to the left. And then there you see the intergalactic tramp globular cluster, NGC 7006, out about where it would be. So let's go back to the times on this. Messier 20, 5,000 years ago, okay, we had pretty organized human society, and they were making things like this goofy statue. 22,000 years ago, we were fully evolved human beings, like these Cro-Magnon people painting a picture of a horse. 195,000 years ago, well, there were early humans like the Neanderthals, and I couldn't find an accurate picture, so I picked this this book cover. Oh, there weren't dinosaurs then. When these things were named, well, the two Messier objects were named in the 1700s, or they were discovered in the 1700s, and they got their names from Charles Messier with his teeny little telescope working from downtown Paris. And the NGC 7006 globular cluster was named in 1888, along with a jillion other objects that we know, as a part of Dreyer's The New General Catalog. NGC means New General Catalog, and it was new in 1888, but we still call it the New General Catalog. So let's go all the way out. We've now left our own galaxy, and so picking a few things that are orders of magnitude away, Messier 31, the great galaxy in Andromeda, its light left, when you see it, that light left the galaxy 2.6 million years ago. Messier 104, it's 42 million light years away. And I pick another galaxy, NGC 4889. I think it's one in the Coma galaxy cluster. It left that galaxy, and it took 400 million years to get to your eye. And then the furthest out thing I've got is a quasar, one of the first ones discovered, called 3C273. That's Third Cambridge Catalog of Radio Sources 273. And it's estimated to be 3 billion light years away. So Messier 31, if you think about this in the structure, it's the closest big galaxy. Messier 104 is part of the Virgo galaxy cluster, and that's kind of the closest big galaxy cluster. NGC 4889 is one of the two main big galaxies at the center of the Coma Galaxy Cluster, which is 10 times further away than the Virgo cluster. And 3C 273 is the beginning of what has been called, may not be accurate anymore, the quasar region. When 3C 273 was first discovered as a radio source, it wasn't really known what it was, and we spent a lot of the last century arguing about what a quasar is. And here's a map of the local group. And here's us and the Virgo cluster and a map of the local supercluster. And over on the other side is the Fornax cluster. And then here's an even wider view between us and the Coma Galaxy Cluster. The Coma Galaxy Cluster is all those little dots are galaxies. And the Coma Galaxy Cluster is part of what has been called the Great Wall of Galaxies, one of the first really large-scale structures in the universe, middle of last century, or I guess that was 1970s. So let's go back to what was going on the Earth when light left it. Messier 31, 2.6 million light years away. Well, 2.6 million years ago, our planet had the earliest hominids. Maybe we had tools back then, maybe we didn't. 42 million years ago, that was the age of the giant mammals, and I picked the Uintatherium, which is just a favorite fossil. It's a big kind of rhinoceros thing from I believe the Middle Eocene area, and his name comes from the Uinta Mountains in Utah and Wyoming, I think. And Uintatherium means beast from the Uinta Mountains. NGC 4889, which is 400 million light years away. Well, 400 million years ago on Earth, we were in the Devonian period, and that's where you had these ugly, scary, bony fishes. You'll notice we skipped right over the Cretaceous Jurassic dinosaur period, and that pains me, but I had to stick with the method, and the dinosaurs got left out. 3 billion years ago on this planet, it's theorized that's when life first arose. So when you're looking at the light of 3C 273, which is a really faint little thing, it's almost magnitude 13. Its light has taken 3 billion years to get here.
Dennis, we have a question.
Oh, please.
The question comes from Brandon Riddell. Is NGC 7006 still orbiting the Milky Way galaxy?
Yes. One of the things that's been discovered in the last 30 or 40 years ago is the Milky Way galaxy, as most large galaxies, has absorbed many other galaxies. There's an accurate count for the Milky Way. There's actually been more work done on Messier 31 because you can kind of see all of it. Here we can only see part of it, looking because it's obscured by dust and stuff. But to the best of my knowledge, yes, it is a globular cluster that was stripped off a galaxy that the Milky Way has absorbed. And in fact, they've figured out some of the galactic mergers in the Milky Way, because they've been able to take the kinematic motions, which you wouldn't think you could measure, but you can, of all the globulars in the Milky Way, and they can figure out, well, these 5 globulars came from a galactic merger, and it basically, the Milky Way absorbed all of its stars and dark matter and dust and stuff, but the globular clusters were kind of their own thing, and so a lot of them have stayed intact after this merger thing.
Okay, I've got another one for you. In the gap section that you spoke about earlier, is it that there's just nothing there, or it's just nothing that we've been able to observe, either due to dust preventing light from getting through, or? Any comment?
Yeah, it's to me, the first thing to think about this is, stars are really, really far apart, and that most of space is empty. Now, we haven't spent, we just now have the Voyagers that are leaving, that have left the solar system. They're now leaving, they've got into heliopause, but that's barely order of magnitude 6. And so we don't know, we just don't observe anything there. And of course, keep in mind this whole distance thing. Well, these are all estimates. The Barnard star, we probably know that really well. Everything beyond that, there's, in fact, until recent years, everything beyond that was in some cases inferred because you couldn't actually measure actual parallax. Now, I think it's the Gaia Observatory has been able to find parallaxes and proper motions for a lot of the stars in our neighborhood. But so I'll say we're pretty sure we know that gap is there and that we're just not observing in it. Now, there could be invisible, non-corporeal alien colonies out there that just don't generate any light or absorb any heat, and there could be something there. But at least in the catalog of things we know about, there's 3 orders of magnitude of distance around our solar system. And so again, the point is that it's the stars in our galaxy are really, really far apart. Any other questions?
Not yet.
All right, get back to where I was. Okay, yeah, we're here with the animals. When were these things named? Well, Messier 31 was known in the year 905 by Arab astronomers as the Little Cloud. So we'll say it was named in 905, though Messier didn't put his number on it until the 1700s. Messier 104, again, part of the Messier catalog, it was named in the late 1700s. NGC 4889, one of the central galaxies of the Coma Galaxy Cluster, was named as a part of the new general catalog. And the 3C273 quasar, it was named in 1959. And this is, it's less of an astrophysical name than, they had started doing radio astronomy and had identified a number of strong radio sources. And this is one of the brighter ones that we see in the radio sky. We've since observed it optically and then, done spectroscopy and stuff. And now know that, no, it's this incredibly bright thing really far away. Let's see. So, I probably should have coordinated with Doug on this before. I have a one-page handout that has all this stuff on it, so you can put it in your observing gear and see how many of these things you can observe. But here it is, kind of tabulated in light years and miles. And of course, we're having to use that goofy scientific notation because the range of numbers is just so wide, from six light years away to Barnard star to the quasar at a lot of miles, 10 to the 22 miles. So
I've got another one real quick. So when you mentioned the Voyager spacecraft and I guess Pioneer 11, are those in that gap now, or?
Yeah, I believe so. I hadn't really thought about it. Let's go back to the picture. Yeah, you see the Voyagers have left heliopause, which means they're probably out I'll use my cursor, probably real close to this little red ring, which is the orbit of Sedna, which is one of the outer solar system objects. And so but they have a long way to go to get to the Oort cloud, which is this kind of donut-shaped thing further out there. And so the two of the missing orders of magnitude are here between the tiny dot of our solar system and the edge of the Oort cloud. And of course, the Oort cloud is it's an inferred thing from observations they've made. There's not really a good map, but it looks good to make it look like a donut.
Okay, thank you.
All right. Oh crap! I've lost my thing. Let me see. Sorry. There. Am I back?
You're back.
Okay. During this Microsoft. So for me, and I did observe this a couple times out at Texas Star Party. Observing them helps kind of understand this cosmic distances. The choices are arbitrary. You could make your own list, use your own, it doesn't have to be base 10. It could be base 6 or 12. People have said that we really made a mistake picking base 10 as the base of our number system, that there are a lot of really good reasons for using base 12, but it never caught on. So some suggestions, if you want to build your own, pick ranges that get the dinosaurs in, use different bases of magnitude like I talked about, and fill in the gaps. One of the times I gave this talk a long time ago, somebody said, well, you could add one more last order of magnitude beyond the quasar. You turn on your TV and watch the snow, and that's the cosmic microwave background. Well, you can't turn on TVs that way anymore. This tells you how long ago the talk was written. But there's probably other ways that us normal people could see evidence of the cosmic microwave background, which would be pretty much as far out as you can get. But I tried to stick to things that we could see and read about in our reference books.
Okay, I've got a question that popped up. If you got a minute.
Yeah.
So the question came in from the email. What might the James Webb Telescope capture?
Oh, well, the James Webb, God bless it. It's no relation. The James Webb Telescope it's following a progression of elevation or of evolution of space telescopes. One of the things that the Hubble did, and several other observatories have done, have pushed for increasing ability to image in the infrared, which you'd say, well, okay, that sounds interesting. But because of the redshift that comes from distance, when the light leaves something out at 3C 273, it's visual light that we would talk about, red, green, and blue. By the time it gets to us, it has been redshifted into the infrared. And so the Webb is not only do you get this massive increase in aperture, but you have a mirror and an optical system that's designed to see stuff in the infrared, meaning it can make pictures of what the thing looks like if you were closer. But if we just look through a telescope, we wouldn't see anything because it's in the infrared. And so, in fact, if you look at some of the recent all sky surveys, they're almost all have a rich infrared band coverage for it, because the further away you get to see what's going on, like in spectroscopy, if you take a spectroscope of the thing, well, if a pattern of lines off a stellar object that say, oh, there's hydrogen in there, well, those pretty, I think they're yellow bands, those would be moved into the infrared, which is invisible to our eyes. So that's one of the big things. I've been meaning to go study the Webb now that it's here, because I suspect it will do optical stuff, but that gold coating on the mirror is designed for efficiency in the infrared.
Thank you.
Okay, I think I'm done.
Okay. Looks like we had one more that came in that doesn't appear to be necessarily related to your topic, but I'll go ahead and ask it anyway. It came from the web, the email. It said, Mr. Webb, you relate a very funny, for us, anecdote about your 1995 trip to Russia for the JSC Oral History Project. Besides visa issues, can you elaborate on our cooperation with the Russian space program today?
Yes. It's funny. A lot of those oral histories are, some old guy who had a big role in Apollo, and he tells war stories of how difficult it was. Mine was flying back from Russia after I'd been detained by Russian customs because I didn't have a multi-entry visa, and I was not allowed back into Russia after visiting Kazakhstan. So you can tell I'm wired and just anxious. Anyway, the partnership with the Russians, it's when you do things with real partners, as we've done on the International Space Station, a lot of politics is always a potential interference, but when you make engineering and operational partnerships, that's durable. So even we've had good and bad relations with Russia over the years since we became their partners, but once you get it's particular. I don't know, the disciplines are all different. Training is 100% cultural, and that's hard to work between two very different cultural partners. Space navigation, orbital mechanics, that's all physics, and those guys met each other and didn't even have to have interpreters. They just went to the board and started writing equations. And so to a certain extent, I pay attention to what's going on the space station, that everything seems to be working really, really well, and that the partnership is strong. We've kind of encroached. The Russians used the International Space Station as a way of generating revenue because we and other countries had to pay them to carry our astronauts up and down, which was actually a thing that was good for geopolitical stability, because we trusted each other and we could afford to pay for it. They could take that and build and launch rockets. Well, now that we have SpaceX and a couple other people on the horizon who can launch our own things, the Russian partner has lost a chunk of income from us. As an American, I'm glad we're not paying them for rockets, and we're buying rockets here in the country. And so that's probably the only structural threat right now, because the Russian Space Agency, it's not viewed as a national priority. It's viewed as a symbol of their prowess. And so they have struggled with funding ever since the Soviet Union fell, because the government had less resources. And so it's been a struggle, but the International Space Station was instrumental in stabilizing their space industry and actually keeping them able to fly. And you've seen recently they launched a new module up, and they hadn't done it in a while, and there were some problems, and the thing went out of attitude control for a while. But I'll wrap up that the partnership has been very beneficial in stabilizing to the U.S.-Russian relationships. And there's always, one side or the other will pick at the other on the political side. Like there was a thing, they had a leak in one of the Soyuz orbital capsules, and there was finger pointing, and they now, every so often when some Russian politician needs to score a point, they'll say, well, it was a crazy European astronaut that poked a hole in our spaceship. And not the case, not the case. But, you know, it's some politicians, all they have to do is get through the news cycle. Any other questions?
Potentially one more here. Let's see. Can you comment on using H2O, CH4, CO2 bands in infrared for atmosphere of extrasolar planets?
Wow. That's kind of out of my knowledge, but the one of the great things about infrared is you can see infrared radiation, and that tells you that. Back up a little bit. We think we're optical astronomers. We look at stuff through the eyepiece, and we use cameras that are basically designed to mimic what our eye sees. Probably 150 years ago, astronomers figured out, oh, if we can work off in that ultraviolet and the infrared things, we can see more, and there's actually just as much information in, if you take, for example, a star, there's plenty of additional information in those other bands. And then we talked a little bit about radio astronomy, and that nobody in the early days of radio astronomy, nobody knew what it was about. But once you put a bunch of PhDs on the thing for a decade or two, you'll kind of figure it out. So yes, I would think it would be reasonable that the Webb would do some planetary imaging, but I have for those purposes, but I haven't done any readout on that. And in fact, I'm sure the infrared bands and ultraviolet have been used to study the planets.
All right, thank you. I'm going to turn it back over to Doug. Doug, you have a go.
Okay, thank you, Dennis, for that very interesting talk. And I'm kind of glad to have Dennis as our speaker tonight. Dennis is kind of a famous person in the astronomy world, so it's great to have him. So thank you, Dennis, for doing that for us tonight. Okay, next up, I have 3 members' minutes, so these hopefully will be quick. We had our first annual JSCAS Astronomy Banquet at Mod Pizza on November 29th, 7 o'clock, and we had 21 members show up. It was a pretty good time. We had fun talking about astronomy and eating pizza. And maybe we'll do this again. I mean, we'll make it a semi-annual event instead of annual event because it turned out pretty good. Next members' minute, 2022, a year of astronomy for the JSCAS. Okay, so a lot of our members have expressed an interest in having extended nights of observing when we go out to star parties. Say you pack up your car and you drive all 6 or 7 hours to get to Fort McCavitt or some other place, and we'd like to have more time once we get out there. So what we're going to do is we're going to try something different this spring. In addition to our Fort McCavitt trip, which is March 31st through April 3rd, 2022, we're going to extend this event by first going to the X-Bar Ranch Saturday, March 26th through Wednesday, March 30th, and then moving to Fort McCavitt on Thursday, March 31st through Saturday, April 2nd. So the X-Bar is actually fairly close to Fort McCavitt. It's 50 miles west of Fort McCavitt, so it's not too far away. And the X-Bar is actually where they have the El Dorado Star Party, and it's used routinely by astronomers throughout the year. Stan Metter, the guy who we work with there, he says that they have astronomers there every new moon of the year except for in December and January. They have cabins available and RV sites. And once we rent a cabin or use RV, the lodge and the kitchen, the dining room is all available for us to use, which is really nice. They have a place you can make food, and they have a refrigerator and everything. And all the cabins have bathrooms and showers and all that. So it's pretty posh compared to a tent camping, which is, what I'm used to. So what you need to do is you need to make your reservations for this event. You go to the X-Bar Ranch website. It's www.xbarranch.com. It's shown here on this slide. And we need to kind of go ahead and get our reservations made. Several of us have already made reservations. And the reason is because the X-bar books up every month, and so we'd like to, get in there and be able to do this. So if you want to go, try to make your reservations pretty soon, either for an RV slot or a cabin, and come out and join us. And we'll have a week of astronomy, and we'll call this the Year of Astronomy for the JSCAS 2022. Okay, last members minute, images from the El Dorado Star Party. So at the beginning of November, myself, and let's see, there was me and Brandon Riddell and Al Mallory and Ron Sterlecker. There may have been some other folks there from our club at the El Dorado Star Party. And I used two different imaging systems. This is actually from a different star party. This is actually from the 2019 El Dorado Star Party, but it's the same thing. So on the left side is that's an 8-inch Ritchie-Chrétien f8 telescope with on a Los Mandy G11 mount. It has a KF A300 CCD based imaging camera that I designed and built myself. And then I use a thin off-axis guider. So that's the imaging system on the left, and that's going to be used for the first two images that I show you. The third image I show you is going to be taken with a 17 to 70 Sigma camera lens at 70 millimeters at f5.6. And that's on a Celestron ASGT mount, and it has a modified Canon 450D camera, which means the filters were changed out to help with near infrared response. And then it uses an Orion 50 millimeter guide scope for guiding. And then the last image I'm going to show you is the same 17 to 70 Sigma camera lens that's 17 millimeters with f2.8, and it's just on a tripod, and this was on unmodified Canon SL3 camera. Okay, so 4 images kind of. All right, so the first one, this is the NGC 2170 area. It's called the Angel Nebula. And this, I put a map on the side to show you where this is. You can see Orion over there. Let's see if I can use my cursor. So there's Orion. And just directly to the left, or east of Orion, this is where NGC 2170, this Angel Nebula is. And it's really close to M42. So M42 is super bright, the Orion Nebula. And so when we go here and you got the Horsehead up here and others, this area is dominated by these. But this Angel Nebula, I just recently discovered this in the last year or so. It's not as popular, but it's a fairly dim object. But once you put enough exposure time on, I think it's a pretty good looking nebula. It has a reflection nebula in, has emission nebula, has dark nebula. And so it's a very interesting area. Now, what I'm hoping to do when we go out to El Dorado, or I go out to the X-Bar this spring, is I'm trying to use a different telescope to have slightly wider field of view, because you can see here over here on the left-hand side, there's a couple reflection nebulae here that I didn't get, but if I can expand this field of view just a little bit, I think I can get more of this. So it's a very interesting area. And but it does take some long exposures. I use 12-minute long exposures for this, which is kind of long for LRGB exposures. The
Doug,
next one, okay, yep.
how wide of a field are you looking for?
This one is actually 38 arc minutes wide, and this is done with the Ritchie-Chrétien I just showed you. And the next one, I'm going to use my Newtonian telescope, which will give me around a 60 arc minute wide. So it'll be roughly 1/3. Okay, if you imagine this thing, it'll be about, take half of this image, and that will expand out roughly half of this image more wide on left and right. So, and I don't want to go too far out, because I still want to get the detail of this. But and my Newtonian is actually my favorite of my imaging telescopes. I think the Newtonian will actually make a very good image of this. Does that answer your question? This one, yeah, this one's 38 arc minutes. I'm going to shoot it at 60 arc minutes when we go out to X-Bar. Is that what you're asking?
Yes.
Okay, good enough. Okay, the next one is NGC 891. This is, if you've ever seen that show, The Outer Limits, this is the galaxy they show at the beginning. So they all call this the Outer Limits galaxy, just because it's used at the beginning of that TV show. This was imaged with the same configuration, the 8-inch Ritchie-Chrétien, same camera as the Angel Nebula. This has 12-minute exposures also. Probably would have turned out a little better if I'd had shorter exposures on this one, but since I was set up for 12 minutes, I went ahead and shot this one at the same exposures as the Angel. But this exposure is just a little too long in this, because some of the stars are saturated. Now, one thing to take note of for you guys doing astrophotography, this central dust region responded really well to deconvolution. What I did is I put a mask on here and did deconvolution actually in PixInsight, and there's a lot of detail in here that came out really nicely using that technique. All right, next one is, this is taken with a camera lens at 70 millimeters and a modified Canon 450D camera. This is on the right-hand side, you'll recognize the Pleiades M45, the Seven Sisters. On the left-hand side, we have the California Nebula NGC 1499. And I took this picture because I like the contrasting colors of the blue reflection nebula of the Pleiades and the red emission nebula of the California Nebula over here. And I've tried to image this before, but I was not all that successful. And the tricky thing on this is getting the camera lens set well so that the stars were small and not blown out and in focus. So I actually used a technique Chris Wells mentioned to us. I asked him one time how he was getting his DSLR pictures so focused so well. And it's actually pretty simple, but Chris told me how to do this and I used it. You take your camera and you put it on live view and then you zoom into a star and you adjust it with that zoomed in image until the star is as sharp as it can possibly be while it's in the live view zoomed in format. And before I tried to use a batten-off mask, which I'm a firm believer in batten-off masks, but I'll tell you for these wide-angle DSLR shots, it actually, the batten-off mask did not work as well for me as using Chris's technique. The other thing on this that helped was I stopped the lens down to f5.6 and that improved the star sizes in the corners, especially the aberrations were much better. And the other thing that I thought was actually very interesting, I tried to take the same image last year at the same place with a 17 to 70 millimeter Sigma lens of the exact same type, but in the old version. And what happened is during this year, that old lens actually broke. The autofocus wouldn't work on anymore. And I sent it to Sigma to have it repaired. And Sigma informed me, they said, well, we can't repair this, is too old, but we'll sell you a new lens for the cost of the repair. So they sent me the new version of the 17 to 70 millimeter lens. And I have to say, it's the same lens, but it's a new version of it. And the optics on this new lens is significantly better than was the old version of the same lens. And there's an article in the January issue of Sky and Telescope where they talk about how the new camera lenses for astrophotography are really coming along, that the optics quality is actually improving quite a lot. And the new versions of these lenses are significantly better than their older versions of the same lens. So just a little tidbit for you there. Okay, and the
Doug,
last, yes.
Question came in. How did you get the Pleiades not to drown out the nebula?
How did I get the Pleiades to not drown out the nebula? I mean, how do I keep the stars from saturating? You don't know what they're asking, do you? Okay.
Check the chat.
Check that. I can't right now. Okay. I think what you're saying is you're probably asking, how do I keep the stars from overdriving the nebula? Okay. It all has to do with exposure and exposure length, your ISO settings, and a lot of experimentation. Okay, like I said, I've actually shot this same image now. I think this is 4th or 5th time I've tried to do this, and my previous ones were utter failures. They were awful and ugly, and I wouldn't show them to you. But getting the exposure length right, these are 4-minute exposures. I tried longer exposures, and even at 5-6-minute exposures, a lot of times your stars will be saturated, so you don't have any star color. If you look in this image, you're going to see colors in these stars. That's because the stars are not saturated. So if you don't saturate your stars, you can actually bring out the colors in the stars. All right. You don't want the stars to get saturated. You want to get them close, but not all the way to saturation. If you do that, you want to have the longest exposure you can, and without saturating your stars. If you do that, then your nebula will come up and your stars won't be saturated. And by using stretching techniques, you can actually bring it up. Now, I will say I did something different that may help you. There's actually a stretch in PixInsight, which is new, called ArcSine Stretch. and I had not used that one before, but it does a really good job of bringing up the nebula without saturating the stars. And this is the first time I've actually used this, but I found it, and I think it's actually a fairly new feature in PixInsight. This one was processed using histogram transforms and also curves transformation, but the arcsine stretch actually helped a lot in that respect.
Okay, the commenter sent back that yes, that's what he was asking.
Okay, very good. But I tell you, I have sympathy for anyone who tries to get this, because it's a tricky one to get. But if you work at it, and you can start where I started, I had to, I was at f5.6, 70 millimeters, and 4-minute exposures, and you kind of start there and go from there. I think I was at ISO 800, either 400 or 800 on this one. But it's a little tricky to get in this one to come out right, but I'm pretty happy with how it, and also in the middle, you'll see there's a dark nebula area too, which is pretty cool. This is actually, these guys in here, even though they look like stars, are actually some reflection nebula. This actually has the NGC 1333 area and an IC 348 areas in here somewhere too. But you can't see it, so it doesn't matter. Okay, the last one here. This is the first time I've done this. I know other people have done a lot of these, and this is really easy. It's a lot of fun. This is a time-lapse video of the Milky Way going over the Eldorado star party. And I'm going to start it here in just a minute. But let me first tell you how I did it. I use a 70 millimeter lens again, set at 17 millimeters. But to find out what your exposure is, I'm just going to put this camera on a tripod. It has no tracking at all. It's just set on a tripod. You can use the rule of 500 to figure out what your shutter speed is. You take 500 and you divide it by your focal length, like 17 millimeters, and I got 29.4 seconds. So I shot these at 25 seconds. The rule of 500 will tell you what's the longest exposure that you can use and not have objectionably smeared stars in your image. Camera's on a tripod, so no tracking. It's really super easy. And then you can just take these still images that you take and you combine them together to make a time-lapse video. I use Corel Video Studio, which I got for free with the camera I have. And it's really, really easy to make these. So I'm going to start this. This was at ISO 3200. Yeah, and 17 millimeters and f2.8, I should have said that. So this is how it turned out. So that is the Milky Way passing over the Eldorado star party. And you'll see these red flashes in there. That's their astronomers that are coming along and shining their red flashlight on me in the middle of the night. You can also see meteors and satellites and all those kinds of things going through the field. This is actually, I think this is Jupiter here, this bright one. That's Venus there. And then Jupiter is coming up here. There's Jupiter. And if you're real quick at the beginning, you can actually find the find Sagittarius, little teapot right in there. This is the center of our galaxy there. Right off the spout of the teapot is where the center of our galaxy is. It's right in there somewhere. Yeah, right there. But if you want to do some easy astrophotography, it's kind of fun. This is something that's really easy to do, and I invite you to try that. So I think that's it. All right. Next up, we have Chris Wells, who is filling in for David for Star Party News. David's out and Chris is filling in, and thank you, Chris, for doing that for us tonight. So I'd like to turn it over to Chris.
Chris, you have a go.
Thank you. Doug, first of all, those pictures are absolutely phenomenal. I love the Angel Nebula. Haven't seen that one before. Thought that was fantastic. And the wide field of the Californian Nebula that I've never really happy about capturing myself, but with Pleiades in there as well. Fantastic. Loved it. Anyway, moving over to Star Party News. This is David's segment, and just filling in for David here. Okay, first slide. First of all, we did have a couple of events. Just seeing a typo here. First of all, we had the Hack Winery on November the 19th. I've got some slides to show on that. And there was also a Hyde Elementary School star party that took place, I think that's meant to say December the 9th, because I think that took place yesterday, if I'm right. Forthcoming events coming up. We've got the Fort McCavett event that has been confirmed. That's coming up on March the 31st. Through to April the 3rd. And we've got a couple of others as well. We've got the South Shore Harbor and Magnolia Creek Golf Course, 2 dates under discussion. So we're certainly getting some more interest here locally on star parties. So as those, as we find out what those dates are, they'll be published on our website. And Hack Winery dates. Hack Winery has been very successful for us over a great number of years now. I think this year we had about 5 or 6 dates, and we're looking for probably 6 dates coming up next year for the Hack Winery. So here are some pictures from the very successful Hack Winery event that took place on November the 19th. We think there was somewhere in the region of 200 people in attendance. So we're getting back to very large crowds of people lining up to actually use telescopes and look and entertain while they're drinking wine. So it's actually a fantastic event. It's one of my favorites. I love it. Many thanks to Bob and Leslie Eaton. Can't really thank myself, but there's also, I will thank Chris Randall, who is there as well, Kevin Timmons and Karen Ward. So here's some pictures of those named. You've got me. I'm goofing off a little bit on the right there. Really, what I'm trying to show is that I've got a shirt with one of the Johnson Space Center Astronomical Society logos on it. So that's what I'm showing off there. Happy Chris Randall taking a sip of wine, and a new member to the club who's actually attended. I know he's attended at least 2 Hack Winery events. Reed was there with a small, I think it's William Optics 61 telescope, and doing some electronically assisted astronomy. There's Bob Eaton with his Muon telescope. As I said, there were 200 or so people there. I really wanted to sneak some looks through Bob's Muon, but just could never get close to his telescope. There were that many people, so I never got to see the delights of Jupiter and Saturn through his Muon that night, but perhaps another night. And is Leslie checking out some dinner as well. Speaking of which, I think with the Hyde Elementary, which I think was clouded out yesterday, but I did see some Facebook pictures of some attendance by Leslie and I think a few other people that were sort of entertaining the kids, I think, inside at that event. So thanks to Leslie and whoever else attended. And lastly, I know David likes to finish off with a funny. So here it is. That's all, folks. Back to you, Doug.
Doug, you have a go.
Okay, Chris, thanks for filling in on Star Party News. Appreciate that. And I think that is it. So our next meeting is January 14th. And we don't know who the speaker is going to be yet, but it's going to be a good one. So I hope you can join us in the middle of January. We'll all be freezing, I hope. And see you then. Thanks for attending.